Hey folks, so we have another problem to work on. We have a problem with 2.1 kilograms of aluminum, and we'd like to know what is the volume of a cube after we have melted it. So we start with our givens. What do we know? We know the mass is 2.1 kilograms. And what do we want to know? Well, we're trying to figure out the volume. All right, so now that we have our volume, we need to know what the equations are. So we have our given and we have our unknown. So what equations are we going to use? Well, so the equation that relates mass to volume is, of course, the equation for density. Density represented by the Greek symbol rho. Density is equal to mass divided by volume. So to figure out the volume, we're going to need to do some algebraic manipulation. We multiply both sides by volume. That, of course, eliminates the volume on the right side because it cancels out. And we have our equation that shows volume times density was equal to mass. But we don't need mass. We're given mass. We need volume. So now we're going to divide both sides by the density rho. And so now we've got our volume is equal to mass divided by density. So as before, we have mass, but we don't have density. So we're going to need to figure out what density is. To do that, we of course are going to go to Wolfram Alpha. So here we have Wolfram Alpha. So we're just going to type in what is the density, if we can spell it right, density of aluminum. And here's what we get. We see it's 2.7 grams per cubic centimeter, just as we've seen before when we've used Wolfram Alpha for this. Okay, so now that we've got our density, what we're going to do is we're just going to plug these numbers in to our equation for volume. And we note that volume is equal to the mass, which is 2.1 kilograms, divided by the density, which we just got, is 2.7 grams per cubic centimeter. But we will notice that we've got a problem because we have kilogram units in the numerator and gram units in the denominator. So what do we do here? What we need to do is convert kilograms to grams or grams to kilograms, either one, but we need to make sure the units for grams and kilograms so that we have the same units so they'll cancel out and we'll get a volume in cubic centimeters. So I'm going to go ahead and convert kilograms to grams here. So what we're going to do is we're going to get rid of the kilograms, and so I'm going to put kilograms in the denominator so it will cancel out here, and that's going to get, then we know there are 1,000 grams in a kilogram. And so if we multiply all of this through, this is going to give us roughly 780 cubic centimeters. And I'll write it in scientific notation. So that's 780 cubic centimeters. So that's what we have, all right? So we've got 780 cubic centimeters as the volume. Now the next question we should ask, and this is a question that's not in the text, but I think from an environmental perspective, it's very interesting, and that is roughly how many cans correspond to 2.1 kilograms. So we've got 780 here cubic centimeters. One of the questions we might ask, of course, is how many liters, just to give this a little bit more perspective so that we know that we're taking these cans and we're crushing them into a cube that's roughly 700 cubic centimeters. Well, we'll take this unit conversion one step further if we want to do this. And let's just convert it to liters because most people have a better perspective on liters. 700 cubic centimeters, of course, is 780 milliliters. So I'm just going to go ahead and write that milliliters because, again, 1 cubic centimeter is equal to 1 milliliter. So that's 780 milliliters, and we know there are 1,000 milliliters in 1 liter. So what we have here is 0.78 liters. All right, and again, a liter is roughly the same volume as a quart. Not exactly the same, but it's pretty close. And you can go ahead and do that conversion if you want. But we know that we've actually taken these cans and we have actually compressed them into a volume that's less than a quart total. Very interesting. So the next step here in this calculation is then just to figure out, well, how many cans are we going to use for this? How many cans are going to correspond to 2.1 kilograms, and that we have actually managed to compress into a volume that's less than a liter. All right, so how do we figure out how many cans we have that's compressed into this 0.78 liter or 780 milliliter volume? Well, we know that we've got, so what's our given? We know that we have 2.1 kilograms. So if we want to figure out how many cans what would be our next step? Well, we would need to know the mass per can, because if we have 2.1 kilograms and we divide that by the mass per can, we could find out how many cans we have, right? So basically, you know, if I've got a particular mass per can, let's call that X. If I divide 2.1 kilograms by X, that's going to give me the number of cans, right? Okay, so how do I figure out what that mass per can would be? How do I figure that out? Well, what do we do when we want to find something? We could do an experiment, and we could take a bunch of soda cans. We could take a soda can and we could weigh it. And usually if we're doing experimental work, we're going to do multiple cans and do an average to determine what we're going to use, because there can be a little bit of variation from can to can, so we want to get an average. But fortunately, somebody's already done this experiment, and I just went out and Googled it and found that typically there are 34 cans in a pound. All right, so of course that's pounds. All right, so there's a problem there that we've got 34 cans per pound, and we've got kilograms. And remember, a pound is a unit of force. And because it's a unit of force, that means that it depends on, it is weight in this case, so it depends on gravitational attraction, as we talked about previously. And that means that the weight depends on the location. So we're going to have to make some assumptions here, which actually makes sense. We're going to assume that the people who determined that it was 34 cans per pound did it on the surface of the Earth, so that we can convert from pounds to kilograms. And so let's go ahead and do that. I'm going to rewrite this as 34 cans per pound. And what I'm going to do is just simply look it up. You can do a conversion, of course, in Wolfram Alpha. What we find is that 1 kilogram is roughly 2.2 pounds on the surface of the Earth. And so what I'm going to do is I'm going to convert this to kilograms. So that means I want pounds to cancel out. I've got pounds down here in the denominator. So when I write my conversion factor, I'm going to want pounds to cancel out. So I'm going to put it in the numerator. So we've got 2.2 pounds per 1 kilogram. And if we multiply that through, the value that we get is going to be the number of cans per kilogram. All right, so we're just going to pull up Wolfram Alpha here to do this. Or you could use your calculator, whatever that might be. And all right, we're going to get a value of close to 75. I'm just going to round it off to 75 because there's a lot of experimental error in these values here. So I'm going to round this off to 75 cans per kilogram. Okay, so that's our important conversion factor here in this particular circumstance. Now, I've got 2.1 kilograms, and so what I can do is just take this 75 cans per kilogram, and remember what I'm trying to figure out is how many cans that I have in this circumstance. So if I multiply it by 2.1 kilograms, and again, you'll see kilograms cancel. And I should have pointed out up here that in this calculation, the pounds cancel, and that's how I get 75 cans per kilogram. So in this case, the kilograms will cancel out. And so when I multiply that out, then I'm going to get a value of roughly 157 cans, close to 160. And really, we should round that to 160 given the imprecision of the information that we have. So think about this. That's 160 cans that we have taken and compressed into a volume that's less than a liter, less than a quart. That's a pretty significant factor change in terms of the volume, and that compression actually is important. Of course, what we like to do with aluminum is recycle it because it is recyclable, but it also just becomes, by compressing it, we have made it far more compact, which means it's easier for transportation, it's easier to use in doing that. So we have taken roughly 160 cans and compressed it into a volume of roughly 0.78 liters. Pretty cool, right? Okay, so this ends our discussion of this problem, so stay tuned for more.